Hello, Math 442ers. I'm here to present a proof of Theorem 4.1. Theorem 4.1 gives us a criterion for when two elements' powers are equal to each other. Part 1 of the theorem says that if the order of an element is infinite, then a to the I equals a to the j if and only if I equals j. Now we already showed part 1. This was problem 7 in chapter 3. Now, number 2, they want us to show that if the order of A is equal to n, then the cyclic group generated by A consists of the identity, a squared, all the way up to a to the n minus 1, and that's it. And a to the I is equal to a to the j whenever n divides I minus j. So first up, we'll prove this equality. Now, as we saw today in class, actually, to show a set equality, we want to show that there's containment both ways. So we want to show that the cyclic subgroup generated by A is contained in that set on the right, and vice versa. So I say that clearly, clearly, a squared, all the way up to a to the n minus 1 is contained in the cyclic group generated by A, because these are all powers of A. So all powers of A are in the set on the right, so this is a subset of this. I hope you agree with that. So I want to show the other way around. I want to show that this is a subset of this. So to that end, I'm going to let a to some power, a to the k, be an element of the cyclic group generated by A. So here k is some integer. And I want to show that it can be written as one of those powers on the right there, either the identity, a squared, or all the way up to a to the n minus 1. So what I'm going to do is I'm going to write k as being equal to n times q plus r, where here 0 is less than or equal to r is less than n. And I guess we've introduced two integers, q and r. So I can do this using the division algorithm. Alright, so now looking at a to the k and substituting in this new power, we get a to the n is the identity, so this is just the identity raised to the qth power times a to the r. The identity at any power is just the identity, so this is equal to a to the r. And since r is in between 0 and n, we're done. So this shows that the cyclic group generated by A is exactly the set E, a squared, all the way up to a to the n minus 1. Something that I think we suspected up till now. Alright, good. So next up we want to show that a to the I equals a to the j if and only if n divides I minus j. Okay, so first I'll prove the forward direction. I'll assume that I have a to the I equals a to the j. So this means that I have a to the I minus j is equal to the identity. So I could write I minus j as being equal to qn plus r, where 0 is less than or equal to r is less than n, using the division algorithm. So, since E equals a to the I minus j equals a to the qn plus r is equal to a to the r, as we saw in the last part of the proof, because the a to the qn is just the identity. We see that r is equal to 0. Well, since r is equal to 0, this means that I minus j is equal to qn. Well, if I minus j is equal to qn, that's the same thing as saying n divides I minus j. Okay, so finally for the other implication. Okay, now to go the other way, we want to show that n divides I minus j implies that a to the I equals a to the j. So if n divides I minus j, well, that means I can write I minus j is equal to n times k for some integer k, and then these two things should be equal to each other, right? So a to the I minus j, or I guess, sorry, when I raise a to each of these two sides, the result should be equal to each other. So a to the left-hand side should equal a to the right-hand side. Well, on the right-hand side, that's the identity, because the order of a is n. So I've just got a to the I minus j equals the identity, and that's the same as showing that a to the I equals a to the j. I can see that by multiplying both sides by a to the j. So we're done!